The basic question. Question A. What is the probability that the vehicle you choose has any other color than the 6 listed? Okay, so to do question A, you will do 1 minus all the 6 probabilities they listed in the chart above. That will equal 1 minus 0.705, which is equal to 0.295, which means that you have a 29.5% probability to choose any other color than the 6 listed. Question B. What is the probability that a randomly chosen vehicle is either silver or white? Okay, to do problem B, you'll take the probability of silver plus the probability of white. So 0.176 plus 0.172 is equal to 0.348, or 34.8%. Question C. When choosing 2 vehicles at random, what is the probability that both are silver or both are white? So to solve this question, you're going to take the probability of silver, which is 0.176, and you're going to multiply that by itself to give you 0.030976. Then you're going to take the probability of white, which is 0.172, and multiply that by itself to get 0.029584. Okay, and then once you have these numbers, you're going to take these and add them together to get 0.0605 as your final answer. Advanced question. Question A. What are the explanatory and response variable in this experiment? The explanatory is the antioxidants, and the response variable is the chance of getting colon cancer. Question B. Outline the design of the experiment. Use your best judgment in choosing the group sizes. Okay, number 1. Divide the people into 4 groups of 216 people each. Each participant will get a number randomly assigned to them. Then use a random number generator to unbiasedly pick the groups. Step 2. Assign each group one of the 4 treatments randomly. Put the 4 treatments in a hat, then select one until all groups have been assigned a different treatment. Step 3. Record and compare the rates of colon cancer among the 4-year period. Question C. Assign labels to the 864 subjects and use Table B, starting at line 118, to choose the first 5 subjects for the beta-carotene, I don't know how to say that, group. So for C, I wrote down line 118 at the top, and for the first 3 numbers, if it fit into our data range, which went up to 864, I included that as one of the participants. So I got 731, 253, 304, 470, and 296. These will be the first 5 participants for the beta-carotene group. Not sure how to say that word. Question D. The study was double-blind. What does this mean in context of this problem? Okay, so double-blind means that both people in the experiment did not know what was going on or which variable they were being tested for. So this means the patient did not know which treatment they were receiving, as well as the doctor did not know which treatment they were giving. It could have been the placebo, it could have been the beta-carotene, it could have been either. This eliminates unconscious bias. Question E. Suggest some lurking variables that could explain why people who eat lots of fruits and vegetables have lower rates of colon cancer. The experiment suggests that these variables, rather than the antioxidants, may be responsible for the observed benefits of fruits and vegetables. Okay, so to do this problem, you're going to need to know what a lurking variable is. A lurking variable is a factor outside of the experiment that is uncontrolled and could affect the data. So basically this could be anything, and this is all up to you, how you interpret this. So this could be anything from how well the person eats to how much sleep the person gets each night. Also things like the age of the participant and if the person drinks alcohol regularly or not. These all could affect the data and all could explain how certain things are happening with the results. AP question. Question A. If a doctor treats a child with an ear infection using Plan 1, what is the probability that the child will be cured? If a doctor treats a child with an ear infection using Plan 2, what is the probability that the child will be cured? Plan 1. So for Plan 1, you're going to want to make a tree chart. And for Plan 1, the tree chart reads that A works 60% of the time, and then A fails 40% of the time. If A fails, then B would work 90% of the time, and B would not work 10% of the time. So what you do is you take 0.6 and you add that to 0.4 times 0.9, and that gets you 0.96, or 96% chance that Plan 1 would work. Okay, so for Plan 2, you do the same thing, you make another tree chart, and this one reads that B works 90% of the time, and B fails 10% of the time. Upon B failing, then you would go back to treatment A, which works 60% of the time, or fails 40% of the time. Okay, once you have that, you would take 0.9 plus 0.1 times 0.6, and that equals 0.96 as well, which means that Plan 1 and Plan 2 have the same exact chance of working out, 96% chance. Question B. Compute the expected cost per child when Plan 1 is used for treatment. Compute the expected cost per child when Plan 2 is used for treatment. Okay, so to find out how much Plan 1 costs, you're going to take 50 and multiply that by 0.6, which is equal to 30, and then you're going to add that to 130 times 0.4, which is equal to 52. And once you add that together, you get that Plan 1 costs $82. For Plan 2, you take 80 and you multiply that by 0.9. Then you take 130 and multiply that by 0.1. And this gets you 72 minus 113, which is equal to a total of $85 for Plan 2. Question C. Based on the results in Part A and B, which plan would you recommend? Explain your recommendation. Based on the results in Part A and Part B, I recommend Plan 1 because the probability that the patient will be cured is the exact same as Plan 2, 96%, which is a very high percentage. And also, Plan 1 costs $3 less than Plan 2. So you'd be getting the same amount of coverage as well as spending less money, which is great.